Can you hear me? Hello? Can you hear me? Okay, I have to ask you a question. How many of you are coders or developers? Don't be shy, raise your hand. Fantastic. So it sounds like the rest of you are not. But still, I'm going to try to make this talk fun for you. This is moving very, very fast. So we are building this technology called formal verification. How many of you know about formal verification? Sounds like few of you already know. So formal verification is, you can see probably that I'm not the youngest person in this room. So formal verification has been along for many, many years. And people say that formal verification will never work. But in fact, in the area of, and actually people have tried formal verification in Web 2. But in the area of Web 3, actually, it's a sort of most interesting domain for formal verification. Because actually, there are a lot of bugs. And in fact, even after you audit code and after you check code, it's very, very hard to see that your code is correct. And here there are a few examples I'm sure many of you heard. I want to point out, of course, the Nomad bridge, a very simple change in the code that costs a big loss of money. I also want to point out the Compound incident, and Compound is a very interesting company. Compound is one of the most secure aware company, and in fact, they are one of the earlier user of Certora. But so what happened is that they actually checked the code with Certora, but after that, the code was changed and was not checked by the Certora. And as a result, a lot of money was lost. So basically, in the area of Web3, you heard earlier in the session, there are actually a lot of tools, and they vary in the complexity and in how much security they are giving you. So the simplest thing you can do and you should do is test your code. And there are fantastic tools for checking the code. For example, Echidna, Foundry. These are very good testing tools and you should just test them. Basically, test your code. If you want to get a little bit more coverage, you can use static analysis. So static analysis basically check more behavior what you can do from testing. And on the right-hand side, you see actually other tools which are more secure. This is what we are working on, basically automatic formal verification. So the Foundry is easy to use, but unfortunately, it is checking the code from an initial state. Therefore, it is sometimes hard to find basically rare bugs with fuzzy. If you want to use static analysis, that's also very useful. This has been used in the web too. The problem with static analysis tools that they have, their precision is not right. They have a lot of cases that they miss bugs, and they have cases that are reporting bugs which are not real. And if you want to use our method, we are providing methods which are more effective in terms of finding bugs. But the problem with these tools, they are computationally expensive. And you're welcome to try our tool. Our tool has a free version. You can try it on our website, but it is a computationally hard problem, and therefore our tool will fail in certain cases. So it is a computationally hard problem, and we are addressing it for the case of Web3. And there are also other tools, for example, used by Certic and runtime verification. These are called interactive theorem provers. So these, they shift the cost to the user. So they make the task of the computer hard, but they make the task of the human impossible. So the idea is it's very, very hard to use these tools, but you can occasionally use that. This is a complementary tool for correctness. So just to sort of show you a picture of what's going on. So here you see on the left-hand side, basically you see the very, very expressive tools, but these are tools which are very hard to use because the human is limited. Sometimes you would need a PhD to prove a single contract. And you see on the other extreme, you see these very easy to use tools which provide lower coverage. Can you hear me now? Thank you. So Satora is building something in the middle. The idea is that we want to build something which is expressive of these expressible tools, but easy to use. So you can use it like unit testing, you can use it like tools, and you can see that it's not as easy as unit testing, but it's tried to be like unit testing. So what do we do in Satora? We have this language called CVL that you are welcome to try. It's a language for writing properties of the code. And then we have technology for checking these properties of the code. And we have three types of the technology. We have the Satora Prover that you can try on our website. We have another technology for checking the CVL, which will be actually open source. And we're also going to build the monitoring for the CVL. It's actually being built. So the idea is these are complementary tools which improve the security of the code. So maybe the most important thing for you to take out if you are not a programmer, that the most interesting part about programs is what we call invariants. So invariants, these are properties which we expect to hold all the time. And they, of course, are not unique in computer science, but in computer science, there is Dijkstra, which is one of the one who basically came with this idea of invariants. And these are properties that you really want to always have, like the bank always wins. Like you always have enough money in the bank to cover your loans. So these are the invariants. And when you work with the Satora tool, you will write invariants. And then the system, you can think about it like a quality assurance tool. It's a system that checks your invariant. And either it provides a proof that your code satisfies the invariant, so this is complementary to auditing. But the most interesting case is it provides a violation. It found a case which is not necessarily starting from the initial state. It could be a rare violation of your code. So maybe this is a very, very simple example. Many of you have seen. This is some code with transfer. And then we run the tool, and you see automatically the tool infers a violation of the invariant that the sum of the balance remains the same. So basically, if you do a self-transfer, you can steal the money. And when you fix the code, we can actually provide the proof that the code is satisfying the invariant. So this is essentially what is provided by the Satora Prover. It's an automatic tool. It's an automatic tool to check invariants. So maybe I can give you a very nice, so we have a lot of users actually, and one of the interesting users in this space is MakerDAO. So MakerDAO has a fantastic team, and they actually started by using other tools, but they switched to our tool. And now they use this tool to check the correctness of the code. And basically, they look into an invariant, and this is actually a tweet by Kurt Berry, one of their developers. So basically what he found out, he used a Satora tool to find a bug in the code which is 4 years old. He basically wrote the invariant, he ran it by the tool, and the tool shows that the invariant is violated in certain situations. So here you see, there is this init function, and this init function actually violates the invariant that the coin is stable. So these are the basic properties of this code. And it shows you automatically, it found the case that the coin is not stable under a certain situation. This code was carefully audited, and people thought they formally verified, and after that, they used the tool to find this violation. Maybe I want to give you another example. I have 5 more minutes, okay? So I want to give you another example, which I think is even more cute, and you can read it in our website. So this is the Trident. It's an exchange by Sushi. And you see, I'm showing you a certain situations here. And the invariant is very, very simple here. You have 2 tokens, and you make sure that if one of them is greater than 0, then the other one is greater than 0. So they're either both 0 or both non-zero. And what happened, the tool automatically found the violation. The idea is that there is a rare case that Alice can burn a holding, and this will break the invariant. So this is a situation which you can think, what's the significance of it? So here I'm showing you the significance of it. I'm showing you a situation in which someone And it's actually a sequence of operation, and this sequence of operation will allow you to completely deplete the contract. So basically, you can deplete the money in the contract by violating this invariant. So this is the violation which was found by our tool. Notice that this is a fairly complex code. It's about 10,000 lines of EVM, and it's actually is able to scale. So that is more scalable method, and it is violated. So I'm almost running out of time, but I want you to somehow give you the feeling of what is this formal verification about. Formal verification is a very, very well understood field of computer science. In computer science, there is the Turing Award. And most of the Turing Award goes to formal method because it's such a hard topic. It's a well understood topic, but there's a lot of myth about this topic. And I want to actually use these minutes left to clarify these myths. So one of the biggest myths of formal verification, and of course, I'm not the only one who say it, but at least in Web3, it's unique. The idea is that formal verification is not for proof. The most value of formal verification is finding bugs. Okay, and of course, people have done it in hardware model checking. I'm not actually saying anything new, but I'm still at least saying something new for Web3. The idea is formal verification. When our tool finds a proof, that's interesting. But the most interesting case that our tool finds a bug. And this is something very useful about formal verification, either before audit or after audit. The second thing, which is the myth about formal verification, that this is a computationally hard problem. Of course it is the case, but the hardest problem in formal verification is actually writing the specification. And that's actually what you see even with our tool. And our tool tried to make it easier for you to write the specification, to write these invariants. Also, another thing that is we are doing, and actually it goes back to the previous talk, is that we have to reason about the exact model. In fact, one of the beautiful things about the Certora prover, and there's a lot of technology around, it doesn't actually reason about your exact model. There is abstraction, and this can actually make the tool works better. So, let me go back. Okay, so I want to say another thing, formal verification, it doesn't replace auditing. It's actually complementary to auditing before or after auditing. And first thing, and the last thing I want to say, maybe the most important thing, formal verification does not guarantee that your code is correct. Formal verification only guarantees that your code satisfies the environment that we wrote. You have to make sure it's increase your security, but there's no such thing as making your code bulletproof. And there are a lot of problems which are not even in the code. Okay. So I'm the end of my talk. I want to end it actually with few things. The first thing is that bug finding is very hard. Whether you use formal verification or not, bug finding is very hard. And formal verification is an interesting case, unlike others, because you start in an arbitrary state. And this makes your code easier. Another thing that I want to say, and actually this is something I wasn't able to cover, but if you look into our white paper, you will read about it. Certora has a lot of technology for basically building this formal verification, and I acknowledge the fantastic team that we have. We have about 90 people on the team, 25 of them with PhDs, and we're actually looking for more. So please, we are hiring and we're looking for more people to help us scale formal verification. We are developing two different techniques to scale formal verification. One is called static analysis and another one called SMT. These are techniques which have been in the academic world for a long time, but getting them to work. So I have time out. I want to say automatic formal verification is a useful thing, and please try our tool, and thank you very much.